In deep learning, we perform a significant amount of linear algebra computations. Tensor libraries such as Numpy, INSUM, and INOPS accelerate our data synthesis and manipulation, model implementation, training, and evaluation. We are done with the development environment, code, and Python. Let's discuss tensor libraries beginning with Numpy. Numpy is an open source, easy to use numerical computing library in Python. It supports most of the common linear algebra operations. In this discussion, our focus is on some mathematical operations that are commonly performed in deep learning. Before we discuss Numpy, let us revisit the list data structure. In Python, there is a data structure that is closely similar to list. It is called tuple. A tuple looks basically like a list, except that it is enclosed in opening and closing parentheses. The differences can be summarized as follows. List is mutable, while tuple is not, meaning the elements in the list can change, while for tuple, the elements are fixed. Both support index and count methods. However, only list supports methods that change its elements like insert or append. In most cases, both can be used. In indicating tensor shapes, it is recommended to use tuple since the values are fixed. Let us discuss some NumPy basics. First, import NumPy. Traditionally, it is alias to NP. To create an array, we use array method. In this example, we created a 2D array of shape 2 by 3. We initialize the array with constant integer values. Please note that in deep learning, most of the time, tensors are floating point numbers, not integers. Verify the data type as int using dtype attribute. This is int64. Verify that the shape is 2 by 3 using the shape attribute. And then lastly, verify the number of dimensions or axes using ndim attribute. This must be 2. For tensor operations, NumPy supports adding a constant to an array. Strictly speaking, this is not a valid operation. In numerical computing libraries, this means adding a constant value to each element of the array. This is called broadcasting, and it simplifies the overall notation. We can also add 2 arrays element-wise. Let us first create another array. In this case, we create an array full of 1s with the same shape as A. We can also do element-wise multiplication, or also known as Hadamard product. If we want matrix multiplication, we can use the matmul method. Note that we can only multiply after transposing tensor B. As a replacement to matmul, Python supports the @ symbol for matrix multiplication. In deep learning, NumPy is a useful tool for data synthesis, manipulation, and visualization. In this example, let us synthesize a noisy grayscale image using NumPy random number generator. The shape of the 2D tensor is 96 by 96 with range from 0 to 255. To ensure that the grayscale image is interpreted correctly, we force the data type to uint8. What if we want to create a 4x4 chessboard pattern? The image is still 96 by 96. There are many ways to create this data. Most of you will think about using a for loop. Recall that white pixel has a value of 255 and a black pixel has a value of 0. Using loops, this is one solution. First, create a white image of size 96 by 96. Then create the middle diagonal pattern, then the lower diagonal pattern, lastly, the upper diagonal pattern. This is inefficient, and it is not easily modifiable to other chessboard patterns like 8 by 8 or 16 by 16. In deep learning, we avoid loops as much as possible since they are inherently slow. We favor parallel algorithms. Recall that thousands of GPU cores can accomplish a task more efficiently if the cores are utilized in parallel. This is an improved version. First, create a function that generates an array with alternating zeros and 1. Then create a 4 by 4 array with alternating zeros and 1. Then repeat the pattern vertically and horizontally. No explicit loops in this code. All methods are inherently parallelizable. This can also be changed to other patterns such as 8 by 8 or 16 by 16. Let us examine the chessboard function. Indices method returns the indices of each element of the array. The return tensor has a shape of 2, 4, 4 or 2 by 4 by 4. The first element or the red tensor shows the indices of the first dimension. The second element or blue tensor shows the indices of the second dimension. Summing across the 0 dimension, we get an increasing number along each axis. Taking the modulo 2 generates the chessboard pattern, which we can upsample using the repeat method to generate a 4 by 4 grid of 96 by 96 pixel chessboard pattern. As an exercise, you might want to find another way to generate this pattern without using loops. Using matplotlib, an image can be loaded into a Numpy tensor. With min method along the RGB axis or the last axis, we can convert the image to grayscale. Numpy can be used to generate audio samples. For example, using sine function, we can generate 1 Hz at sample rate of 22,050. Numpy is a useful linear algebra library, but it has its own limitations. In particular, it is not designed for GPU execution. For that, a direct replacement library like QPy is recommended. Numpy has different methods and APIs for different tensor operations, making it hard to remember which function to call and what syntax to use. Complex linear algebra operations on multidimensional tensors require several function calls to implement in Numpy. For both cases, einsum and einops are recommended. Thank you for listening. The Jupyter notebook for this discussion can be found in the GitHub.